Hello out there, welcome again to this tutorial on sequences and series. In this video, we'll be looking at geometric progressions. Consider the following. A, we have a sequence of 1, 3, 9, 27 and so on. B, 16, 8, 4, 2, 1 and so on. We said in our previous tutorial that these are examples of infinite sequences since it has no end. Can you list the next two terms in A and B above? Starting from A, we have to study the sequence that we have 1 and the next term is 3, the third term is 9, 27. So if you look at it, you discover that 1 times 3 gives 3, 3 times 3 gives 9, 9 times 3 gives 27. So each term is obtained by multiplying the preceding term by 3. Therefore, we will have the next term to be 27 times 3, 81 times 3, 243. And so on. So these are the next two terms of the particular sequence in A. For B, we have a 16, 8, 4, 2, 1 and so on. If you look at it, 16 multiplied by half gives 8, 8 multiplied by half gives 4, 4 multiplied by half gives 2 and so on. So 1 times half gives half and half times half gives 1 over 4 and so on. These are the two terms of the sequence in B. The sequences above are geometric progressions and the short form is GP. They are geometric progressions in the sense that it is multiplication of a particular constant to give the next term of each of the sequences. In each case, any term of the sequences is defined by Tn equal to a raised to power n minus 1, where n is the number of the term, a is the first term, and r is the common ratio. For the common ratio, the particular constant for which we multiply by the preceding term to get the next term. We told you in the previous tutorial that this Tn, depending on the material you are using, so it could be UN, it could be AN, it could be NTH, and so on. So we'll now be going ahead to solve some examples. Example 1. Find the 11th term of each of the following GPs, that is geometric progressions. So we have A, 1, 3, 9, 27 and so on, B, 16, 8, 4, 2 and so on. So what we do here, we already have our nth term, that is the general formula for geometric progression to be a raised to power n minus 1. Now for A, we have to identify our A, our R and our N. So we have A to be 1. We already know from the previous slide that our R is 3. So by multiplying 1 times 3, 3 times 3, 9. But we should also note that R is T2 divided by T1. That is 3 divided by 1, or T3 divided by T2, 9 divided by 3, which will still give us a 3, and so on. Therefore, our R is equal to 3 and our N, as given in the question, is 11. What we are looking for in this problem is T11. So we have our T11 equal to A. Our A is 1 times R. Our R is 3, then raised to power 11 minus 1. And that will give us 1 times 3 raised to power 10, since 11 minus 1 gives 10, and 1 times 3 raised to power 10 gives 3 raised to power 10. This is in index form. If you are to give your answer in ordinary form, you have it as 59,049, which represents the 11th term of the geometric progression represented in example 1a. Then we go to example 1b. Our first term here is 16. Our common ratio, which is T2 divided by T1. This is T2 8 divided by T1, which is 16. R will give us 1 over 2, and our n still remains 11. Now to find our T11 for this sequence, we have our A to be 16 times R, which is 1 over 2 raised to power 11 minus 1. If you have a particular problem like this, what should come to our mind is expressing the values you have as index form of a particular number. Like if you look at it, 16 can be expressed as index form of 2, 1 over 2 can be expressed as index form of 2. So we have it as 2 raised to power 4 times 2 raised to power negative 10. Since 1 over 2 is 2 raised to power negative 1, and 11 minus 1 is 10. So we have it as 2 raised to power negative 10. Please check our videos on Onina resources to get the concept of indices. We've treated it fully there. Now we apply law of indices. Since they have the same basis, what we do is we add the indices, since this is multiplication. So 4 plus negative 2 will give us negative 6. We'll now have this as 2 raised to power negative 6, which gives 1 over 64. Since 2 raised to power 6 is 64, and because of this negative index, we have it as fraction. And that's the end of solution to example 1. And we go to example 2. For example 2, find the nth term and the number of terms in each of the sequences. So starting from our formula, we have Tn equal to AR raised to power n minus 1. And from example 2a, how do we identify if the progression or the sequence is an AP or GP? If you look at it, we say 4 divided by 2 gives 2, 8 divided by 4 gives 2. So if you use the formula for calculating the common ratio and it gives you a particular value for all the formula we gave you on common ratio, then it is there you know that, oh, this is a geometric progression. So we now go ahead with A. Our first term here is 2. Our common ratio is 2, since 4 divided by 2 gives 2. And we have our last term here, L, to be 1024. Remember, this formula is also for L. We can remove this Tn and it becomes L equal to AR raised to power n minus 1. But specifically, we are looking for nth term and the number of terms. So for nth term, which is Tn, we just substitute into the formula our A and R, since we don't know n. Then we simplify. So we have it as 2 times 2 raised to power n minus 1. We can write 2 as index form of 2. That will give us 2 raised to power 1 times 2 raised to power n minus 1. Simplifying this, following the appropriate law of indices, we have 2 raised to power 1 plus n minus 1. And 1 minus 1 gives 0. So we have our final answer to be 2 raised to power n. So that is the nth term of this particular sequence represented in 2a. Then we go to the number of terms in the sequence. It is there we will now use L equal to r raised to power n minus 1, and our L is 1024 equal to 2 times 2 raised to power n minus 1. We then express every term as index form of 2. 1024 is 2 raised to power 10 equal to 2 raised to power 1 times 2 raised to power n minus 1. So from here we have 2 raised to power 10 equal to 2 raised to power 1 plus n minus 1. Since this is multiplication, this will now give us 2 raised to power 10 equal to 2 raised to power n. Since if you collect the like terms, 1 minus 1 gives 0, then plus n gives n. So from here, since the bases are equal, therefore the indices are also equal. So we have n equal to 10. So we are done with example 2a. We've found the nth term, which is 2 raised to power n, and the number of terms is 10. So we go to example 2b. For 2b, we have our a, which is the first term, to be 6, our r to be 1 over 2, since 3 divided by 6 gives half, and our last term is 3 over 32. So our Tn is r raised to power n minus 1. Our a is 6 times half raised to power n minus 1. We can express this 6 as 3 times 2, where we are only interested in the 2. So we have it as 3 times 2, then times 2 raised to power negative 1 raised to power n minus 1. So we might not be interested in expressing 3 as index form, so we keep that one, and 2 is 2 raised to power 1 times 2 raised to power negative n plus 1. If you use this to multiply this, following one of the laws of indices, so from here we'll see that we have 3 times 2 raised to power 2 minus n, since 1 plus 1, because we are adding the indices since this is multiplication. So we have 1 plus 1, which gives 2 minus n, and this is the highest we can write here for the nth term of the sequence represented in example 2. We now go ahead to find the number of terms using L equal to r raised to power n minus 1, and our L here, which is the last term, is 3 over 32 equal to our a is 6 times 1 over 2 raised to power n minus 1. This 3 over 32, I can have it as 3 times 1 over 32, and expressing 1 over 32 as index form of 2, we'll have it as 2 raised to power negative 5. So that we'll have 3 times 1 over 32, and we said 1 over 32 in index form of 2 is 2 raised to power negative 5. Then also this will be 3 times 2, then times 2 raised to power negative 1 raised to power n minus 1. So you see that this 3 here, we cancel this 3. So we'll be left with 2 raised to power negative 5 on the left hand side, and this is gone with this. So we have equal to 2 raised to power 1 times 2 raised to power negative 1 plus 1, after applying the law of indices, where we multiply out the indices here. So that we will now have it as 2 raised to power negative 5. So that on the right hand side now we have 2 raised to power 2 minus n, as we simplified here. Equating the indices here, since the bases are equal, we have negative 5 equal to 2 minus n, where n is equal to 7. if you simplify this equation. So we have n equal to 7. And that's the end of solution to example 2b. We'll go to example 2c. For c, we have our first term to be 1 over 3. And the common ratio is 3. Since 1 divided by 1 over 3 gives 3. The last term is 729. So to find our nth term, that is the Tn, we'll have 1 over 3 times 3 raised to power n minus 1. 1 over 3 is 3 to the power of negative 1, then times 3 raised to power n minus 1. So here we have 3 raised to power negative 1 plus n minus 1. Applying law of indices. So we have final answer as 3 raised to power n minus 2. Since negative 1 plus negative 1 gives negative 2, and we have our n here. And now we go ahead to find the number of terms in this sequence. So our L, which is 729, is equal to A, 1 over 3 times 3 raised to power n minus 1. 729 is expressed as index form of 3 as 3 raised to power 6 equal to 3 raised to power negative 1 times 3 raised to power n minus 1. 3 raised to power 6 is equal to 3 raised to power negative 1 plus n minus 1. The right hand side will be simplified as 3 raised to power n minus 2. So equating the indices here, we have 6 equal to n minus 2, where n is equal to 8. That is the end of solution to example 2c and the entire example 2. We now go to example 3. For example 3, the first and seventh terms of a GP are 3 and 2,187 respectively. Calculate the common ratio. So still remembering our formula, what are we given in the problem? We are given the first term to be 3 and the seventh term, which is T7, to be 2,187. Bringing in our formula, Tn is AR raised to power n minus 1. Remember, we are given T7, which means n is equal to 7 there. So 2,187 will be equal to 3 times r, we don't know r, raised to power 7 minus 1. To simplify this, r raised to power 7 minus 1 is r raised to power 6. 2,187 divided by 3 we give 729. And expressing 729 as index form, we have r raised to power 6 is 3 raised to power 6. Since the indices are equal, the bases are also equal. Therefore, r is equal to 3. And that's the end of solution to example 3. We go to example 4. For example 4, a geometric sequence has its common ratio and fifth term as 5 and 125 respectively. Work out the first term. From our formula here, we now look at what we are given. We are given the common ratio to be 5 and the fifth term, T5, to be 125. And we are looking for A, that is the first term. Since T5 is 125, we can say 125 is equal to A, we don't know A, times 5 raised to power 4. Where are we getting 4 from? 5 minus 1, 4. Remember that? 5 raised to power 4 is 625A. So this is 625 times A gives 625A, making A the subject of the relation. we have it as 125 divided by 625, giving A to be 1 over 5. 125 times 5 gives 625. So that is the solution of example 4. We then go to example 5. Example 5, the fourth and the seventh terms of a geometric progression are respectively 189 and negative 5103. Calculate the first term and the common ratio. So we still remember our formula for nth term of geometric progression. We are told that the fourth term, that is T4, is 189. Remember, the general formula for T4 is AR raised to the power 3, and also we are given T7 to be negative 5103, and the general formula for T7 is AR raised to the power 6. We can now label this as equation 1 and label this as equation 2. So from here, we can say equation 2 divided by equation 1, then A will go, so that we will now be left with R raised to the power 6 divided by R raised to the power 3, which is going to be R raised to the power 6 minus 3, and that will give us R raised to the power 3 equal to negative 5103 divided by 189, and that will give us R raised to the power 3 equal to negative 27. So since this can be expressed as negative 3 raised to the power 3, so that our R is equal to negative 3. Our R is negative 3. Please, if you are having problem solving these exponential equations, check our videos on Oninabu resources. You see indices. Watch all the videos on indices. It will give you first-hand information on how to work out these problems in this tutorial. So we go ahead to find A. We put R equal to negative 3 in equation 1. So we have 189 equal to A negative 3 raised to the power 3. Negative 3 raised to the power 3 is negative 27. And this will give us negative 27A equal to 189, where A is equal to 189 divided by negative 27, and that gives negative 7. So we have done justice to this problem, and the first term is negative 7 and the common ratio is negative 3. That's the end of solution to example 5, and this is the end of this tutorial. I hope you enjoyed it. Please check the description section of this video on our YouTube channel to get the link to the playlist containing all the videos on sequences and series. See you in the next lesson. Till then, goodbye.